Okay, this is problem 9-67. Here we want to find out what the principal stress and maximum in-plane shear stress will be at B on the cross-section here at AA. I drew basically an axis system at this point here. What we're going to do here is just sum up all the forces, sum up all the moments, and set them equal to 0. So we sum up all the forces in the x direction here, and I got mine going this direction as far as the positives go. I sum up my forces in the x direction. I'm going to get 450 plus, we'll call this our fx, plus fx is equal to 0. So in this case we would know immediately, and I'll just write that like this. This would be going back 450 newtons back this way. So fx here would be equal to negative 450 newtons. We sum forces in the y direction here. I got y going up. In this case I have no forces in the y, so I just set that equal to 0. And I didn't have an arrow going, so we're good there. I sum the forces in the z direction. I set them equal to 0. The only thing I have going along the z direction is going to be the 300. So that'd be 300 plus my Fz resultant force, and I'll get Fz is equal to negative 300 newtons. So I just come back here and I'll make this 300 newtons. Okay, now do the moments, and the moments you're going to be a little bit more careful about. We'll take the moments around x and set that equal to 0. So if we're taking moments around x, we're looking for y and z forces. So if I'm taking it around, the only thing I'm going to have is a z force. X force cannot create a moment around its own axis. So when I do this one, I'm going to get 300 times 0.2 plus my moment that's going back the other way. It's going to make it equal to 0. So we get mx in this case would equal to the negative 60 newtons per meter. So we come back here and we'll call this our mx of minus 60 newtons times meters. You can tell right now that's going to cause a torque around this. So we could just say that's equal to the torque. Do the same thing here. We sum the moments around the y-axis and set that equal to 0. So when we do that, we're looking for x and z forces both. So if we do that, then we're most likely going to have them creating moments, each of these. So when we do it around that, we will have 300 times 0.3. Alright, so we got 300 here, and it's not this 300 here, it's this 300 times this distance here. Right, and then we'll do, so that one's, the 300 is going to cause it to move this way here around the y-axis, and then we're going to have the 300 times the, the 450 times the 0.3 going back the other way, so we need to make that. So be careful with the signs, that's all. In this case we get 45 Newton times meters. And we come back over here and then we'll just label this value as our 45 Newton meters. We do the same thing here. We sum the moments around the z. Let's go down, give myself a little bit more space. We set that equal to 0. Again, when we're doing moments around z, we're looking for x and y forces. So the only thing that we're going to have is the 450. So it is a The 450 is an x force, so we're looking for a y distance, so it has to be times 0.2 plus the moment that we have at z is equal to 0. When we do this, our moment at z, we go to minus 90 Newton meters. And we'll label this as 90 Newton meters. Alright, so now we have everything we need to do. From this point, we're going to have to do our section properties. Properties. Obviously, the area of this, that's a tube, has two different diameters. Do that, we do pi times the big R squared minus the inside squared. That would give me that value here. And we'll run this one, our moment of inertia around the y would equal to pi over 4 times 0.03 to the 4th power minus 0.02 to the 4th power. And then we'd have to do polar moment inertia, and that gives me pi over 2 times 0.03 to the 4th minus 0.02 to the 4th value. Okay, and we will run those values very quickly. Okay, that's going to give us values here of 1.57 times 10 to the minus 3, and that'll be meters squared. This one here, I ran it. That's going to give us 5.105 times 10 to the minus 7th meters to the 4th. And the third value is going to give us 1.021 times 10 to the minus 6 meters to the 4th. Okay, then what I did is I drew kind of a blow up at the cross section. I went ahead and put all my different moments and my forces coming across. Now we want to find out the stress that's occurring at point B. Now, looking at the picture, this moment here cannot create any stress at B because it's just the moment around here. There's no C value coming out of here. My distance from the centroid up is going to be 0. So to find my stress, we can say the normal at B is, and I got all these moments going back the way the forces are oriented on the part itself. Here I will have 450. This is going to cause a tensile strength here, so that's going to be 450. All we have to do on this one is divide it by the area, and I go back up to here, so 1.57 times 10 to the minus 3. And now the moment, you notice here that the moment right here is causing compression around this axis, so we will make that negative. And then the distance, the moment arm from here to here, being the C value, we're doing MC over I, would equal to 0.03. Again, all we're going to do then in that case is divide that by the moment of inertia, which we said was 5.105 times 10 to the, what I say, 7th. When you do that, you'll get the B stress. Gives you a value of compression And we can make that, you can make that negative or just put compression. Just gotta make sure you note that. Alright, so now the only other thing that you got taking place here is, so let's just kind of check off what we've done here so far. We've done this force here, so we're done with it. And we've done this one here, we're done with it. Alright. Now, the other thing that we would have on this one is just going to be our torque. So we can say using TR over J equal to the torque value here. Then the only torque that we have that's occurring on this piece is going to be this torque right here, or this moment around here, 60. Let's go down here so that we can say the shear is going to equal to 60 newtons. My R value here would be the distance out up to the outer fiber, which would be 0.3, divided by the polar moment of inertia. And the polar moment of inertia 1.021. Times 10 to the minus 6. And that gives us a value of 1.763 megapascals. Alright. So now let's see what we've done. We've got this one done now too. Again, this is just kind of going to work through this methodically. Alright. The reason you do not have to consider the 300 is because this fiber is out at the outer edge. And remember, when you do stress at any point, you got to have a Q value. So if we were going to deal with this, we'd be dealing with VQ over IT. But in this case, Q is going to equal to 0 because you have no Q area out at this outer fiber. That's why this one you do not have to consider. And we said this one too we did not have to consider because here you had no C value. So these are your two stresses. Okay, so now I'm going to grab a little element, and all I'm going to do is I'm going to look in, like looking in here, and grab just that little element. I'll grab that and I'll make that into a square. Alright, and when I do that, what I have here is I had compression. So I immediately show this as compression coming back this way here. So this is compression coming back this way here. Let me scroll those down so they're getting a little bit better here. Make some room for my shears. Okay, and we know that this is shearing up here. So when I do that, then I'll have a shear coming like this. Shear coming down this. This comes back this way. And this comes back this way here. We will label these values here as 1.763 megapascals. Here we'll create this as our normal X. And our normal X in this case would be the value here, and you got to make sure you get the you got to make sure you show this with the correct sign. So I got compression, that's why I got to make this negative. Okay, now we're ready to generate using more circle. So we just label everything we know. Our normal of X is minus 2.358 megapascals. Our normal Y is equal to 0. Our shear is equal to negative 1.763 megapascals. We draw our two lines here. Again, we put our normal on our X axis. We put our shears down here. Anything goes this way is positive. Anything goes this way is positive. Alright, so first thing to do is find the center of the circle, and remember the center of the circle is going to be normal x plus normal y divided by 2. You're just doing the average of those. So you take this plus 0 divided by 2. That gives you a value of negative 1.763 megapascals. Alright, so what I'm going to do to give myself some room, come down here. I'm just going to shift this axis over because I know I'm going to have to go back to the left. Like this. And I'm going to give myself lots of space here. Move this out of the way. I'm just going to move this over too. Alright. So now to create more circle, you would go over negative 1, sorry, you go over, oh, I labeled that one wrong, sorry about that. Let's fix the shear value. That's incorrect, sorry about that. I should have caught that. That's what I calculated earlier, and that was negative 1.179 megapascals. Alright, so now we would come over negative 1.763, that's the center of the circle. Make that our center. I'll create an axis system here. Oops, do that again. Sorry, I'll try to go right through that if I can. Alright, there's my axis system there. So now what you would do, you go back 2.358 over to here. You put a value here. This would represent negative 2.358. Now the shear is negative 1.7, so you're going to go up along here. Remember, you're going up because it's negative, and you put a value right there. That right there is going to give you the radius of your circle from that point to that point. Okay, from here we can draw our circle. Right there, and now to get our radius. Our radius is going to be using basically Pythagorean theorem here. We know from this distance to this distance, and again we need to label that so we don't make a mistake here. That's going to be negative 1.763. So our radius in our circle here would be this distance squared, which will be negative 2.358 minus this one, because it's going to give me this distance here. We will square that distance, and then we'll do plus the shear stress, and we said that was negative 1.179. We'll square that. We'll take the square root of that. That gives us my R value. And my R value here would be 2.121 megapascals. Okay, that's the distance from here to here. Alright, we're slowly getting this part done. Now, to find my in-plane, to find my principal stresses. My principal stresses are always going to occur at this point here and this point here. Okay, to find this value, what I'm going to do is I'm going to take this one here, which is minus 1.763. It goes from here to here, and now I'm going to go the radius again. So the radius in this case, since we're going to the left, is going to be negative. So I get negative 2.121. I will add those values together there, and I'll get about approximately negative 3.30 megapascals. So that's going to be this value right here. Now to find this one here, we start out at negative 1.763, but now we're going positive. We add the radius, and that gives us a value of 0.942 megapascals. So this will give us principal stress 1, and this will give us our principal stress 2. And let's circle those. Alright. And then to find your shear stress, your shear stress again is always going to occur at these orientations. Here and here. So this value here is going to be nothing more than the radius. In this case, 2.12 megapascals. And that's it. And again, and you could go back through and do all the principal stress, do the correct orientation if you needed to, by finding out what this angle would be here, and because this right here would give your principal angle being 2 theta principal. This is 2 theta shear, and you could work out that way too. Alright, so good problem. Fairly complex, but I think if you follow these steps, you should be fine.